Hello, hello, hello. So, all right. We finally have gotten ourselves to radios. This is going to be fun. So, radios basically allow us to draw together all of the good things that we've been learning about for the entire semester. And here is effectively a list of all the stuff that's going to end up going into this discussion. So it truly is going to be a cumulative review extravaganza, and my picture is hiding the woohoo, but in fact, this is definitely a woohoo kind of an experience. So let us begin. There are two circuits that are going to be important to us. One having to do with the circuit that is at the radio station, and the other is the circuit that's wrapped up in your radio proper. So we're going to start with the radio station. So the first thing that you need to know is that radio stations have an oscillator that put out a single frequency. And in fact, they tell you what that frequency is. When I was a kid, there were two rock and roll stations in the area, in the Pasadena, California area, San Marino, California area. One of them was KRLA. The other one was KFWB. KFWB turned into a news station, but at the time when I was a kid, it was a rock and roll station. And they had this little ditty that they would play on the radio, and it was KFWB, Channel 98. That voice. And so I would be in my car and I would turn on my AM radio and I would take the little tuner and I would put the little pointer on 98 and there would be KFWB. I was not very astute as a kid. If I had been, I would have noticed that on the face of that radio dial was actually the units for the numbers. And in fact, the units, if I had looked, would have been 10 kilohertz. So kilo is 1,000, 10 kilohertz is 10,000. And what that actually would have been telling me was that that radio station would have been using a frequency of 98 times 10,000 or 980,000 cycles per second. So KFWB's single frequency plus a little slop on either side. But generally, their single frequency to transmit on that was given to them by the FCC was 980,000 cycles per second. And in fact, that's what the call numbers tell you, that they're telling you what the frequency is that they're transmitting on. So there's my example. Ms. Dunham, who is the other physics teacher at my school, she is very much into the Dodgers. And in fact, apparently the Dodgers transmit at 5:70 a.m. Their frequency apparently is 570,000 cycles per second, because apparently her radio has units of kilohertz, not 10 kilohertz, but whatever, minor point. So anyway, the point is that you've got this oscillator here that is oscillating merrily away at a really high frequency as far as you're concerned. And there's only one. So there's got to be some clever way that they can put information onto that signal. And that's what this stuff is all about. So there's electronic stuff at the station that allows them to put onto the signal the information that they want to go to your radio that you ultimately end up hearing. And we'll talk about how all that works in a while, but not now. The other parts of this setup, you need a transformer that takes that stuff, that information, and transfers it over to an antenna. And then you have an antenna, and this is the symbol for an antenna. Now, we need to talk a little bit about the antenna. Oh, by the way, the radio frequency range is from 500,000 cycles per second to 1.7 million cycles per second. So you can see that the Dodger radio is right down at the bottom of the frequency range available for radio frequencies. And you'll understand why here shortly, why this is the range. There's a very good reason why it can't go below 500,000 cycles per second. And we'll talk about that. So anyway, we need to talk a little bit about this antenna. and what's going on with the antenna. So you need to remember that you're going to end up having, charge oscillating up and down onto this antenna at a frequency of 980,000 cycles per second if this happens to be KFWB. So let's think a little bit about what that means. So the first thing to think about is that if you have positive charge on the antenna at a particular instant, what that's going to do is it's going to end up generating an electric field around the antenna. And if positive charge will tend to produce an electric field that's pointed away from the antenna, if at some later point in time the net charge on the antenna is negative, the electric field will end up pointing towards the antenna. Additionally, because charge is running up onto and off of the antenna, the amount of charge will be changing. So not only is the direction of the electric field changing, but its magnitude is changing. So you have this alternating electric field in the vicinity of the antenna as a consequence of the fact that you have all this charge running up and onto and off of the antenna. What you additionally have, when you have charge in motion, you have magnetic fields. So you additionally have, as the charge is running up onto the antenna, and a magnetic field in one direction, and as it's running off of the antenna, a magnetic field in the opposite direction. And again, there are going to be times when you have lots of charge flowing on and times when there's not very much charge flowing on. So the magnitude of the field is going to be changing along with this direction. And so in addition to this alternating electric field around the antenna, you're also going to have an alternating magnetic field that in fact is going to be at right angles to the electric field. So the electric field is going to be right straight out. The magnetic field is going to be into the page where my little cursor is, or out of the page. They're at right angles to one another. And this disturbance is just kind of hover around the antenna. And so if you're at low frequency, like 20 cycles per second, which this would never be, but let's just say it was, there's plenty of time for an electric field that's oriented this way to collapse down on itself and reorient itself in this direction. And so what would happen is this disturbance around the antenna would just kind of stay around the antenna. You take the frequency up higher and higher and higher and higher, and sooner or later, you're going to get to a point where there's not enough time for the electric field that's set up due to a particular configuration. There's not enough time for it to collapse down onto the antenna so that the new field that's been generated by the new charge motion can set itself up. And it turns out that the frequency at which this happens is about 500,000 cycles per second. So if you're below 500,000 cycles per second, there's enough time for the electromagnetic field around the antenna to, at a particular instant, collapse down onto the antenna so that the new field can set itself up. If you're above 500,000 cycles per second, there's not enough time to do that. And so what ends up happening is that the disturbance does what's called flipping off. And they're moving at 3 times 10 to the 8 meters per second, which shouldn't be a surprise because radio waves are a part of the electromagnetic spectrum. So this is the reason why the radio frequency range is between 500,000 cycles per second and 1.7 million cycles per second. The lower end of the range, if you go any lower, you aren't going to get the flip off. So this electromagnetic disturbance, that's generated at a given instant that has flipped off, will end up leaving as a wavefront. It will have a certain amount of energy per unit area associated with the wavefront. And as the wavefront gets bigger, that energy density will diminish. The wave will never die out, though, but the energy density diminishes with time. This is fortunate. Otherwise, you would have, stations in New York swamping, Kentucky and California, and you don't want that. But that doesn't happen because a signal being generated by a station in New York, its energy density will die out as the wave moves outward. Just as a kind of interesting side point, though, if you happen to live on a planet that was 70 light years away from Earth, and if you had the technology to be able to pick off electromagnetic waves with really, 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 really low energy densities, it means that you could pick off the waves that were generated by the broadcasting of the first runs of I Love Lucy back in the 1950s. And in our year 2020, you could be watching first run I Love Lucy shows, because that's the amount of time it would have taken the wave to get from here to there, 70 years. Pretty cool. Again, pretty spectacular technology to be able to do something like that, but still. Anyway, so the FCC has restricted the power output for radio stations so that they don't swamp stations that are sort of out of their area. There was a superstation when I was a kid down in Mexico that could actually reach all the way up to Washington, but it's not around anymore. And so the question arises, once this electromagnetic wave has left, what happens then? And which brings us to circuitry that's inside your radio. So the first thing we need to talk a little bit about is what happens on the antenna of your radio. So you have this electromagnetic wave that is passing by, and it's this continuous wave, this continuous electromagnetic disturbance. And because your antenna is made out of metal, the charge carriers in the metal will respond to the electromagnetic wave. If the antenna is just a straight piece of metal, it will respond to the electric field component of the electromagnetic wave. If your antenna happens to be a loop, a circle of metal, it will respond to the magnetic field part of the electromagnetic wave. Remember, changing magnetic fields passing through a coil will end up inducing an EMF, which will motivate charge to flow. So you can actually use a coil as an antenna to pick up, a signal. But most radios have straight antennas. And so the charge carriers in your antenna are going to end up responding, and they're going to end up jiggling back and forth depending on what the electric field is doing that's passing by. And this is where things get really pretty cool. So think back to the sending unit. What you had at the sending unit was this oscillator that was oscillating at really, really high frequency. You put information on that signal, used a transformer to get it onto an antenna. And what happened on the antenna is that you had charge carriers that were jiggling in such a way as to generate this electromagnetic wave that moved out. The electromagnetic wave moves out, it passes by your antenna, and as that electromagnetic wave varies, it ends up making the charge carriers in your antenna move, and they jiggle. And in fact, they will jiggle in exactly the same way that the charge carriers in the sending antenna were jiggling when they generated the electromagnetic wave in the first place. Which means you have basically sent jiggle information from the sending antenna to the receiving antenna via this electromagnetic wave. Which, you think about it, is really clever. I mean, that is very, very, very cool. And in fact, I've got this little breakout video that I'm going to show you that's actually going to show you a sending antenna transferring information or energy to a receiving antenna, and you're going to see that little video right now. So give a watch. Okay, we're back. So anyway, so that's the deal with our antenna. That's what our antenna is designed to do. It's designed to pick up this electromagnetic wave with all this information on it. Now, there's a problem, though, and the problem is that you don't just have one station doing this, you've got a whole bunch of stations doing it. So you've got this superposition of jiggle going on the antenna due to the superposition of all of these electromagnetic waves that are passing by as a consequence of the fact that you have all these radio stations that are transmitting in your area. And so the question arises, how do you select out just the one frequency that you're interested in? And that's where this part of the circuit comes in. This is called the tuner circuit. And basically what the tuner circuit does is it allows you to select out just one frequency. And the way it does it is really quite clever. So you have all these different frequencies that are oscillating on the antenna. They will all, via this transformer, be put into this tuner circuit. Except if you look at the tuner circuit closely, you'll notice it's made up of some inductance and some capacitance. And you've run into a circuit like that recently. And if you remember, circuits like this have a natural frequency that they want to oscillate at. So if the signal that has been put in here happens to match up with that natural frequency, that signal will proliferate. If the signal that has been transferred in does not match up with that natural frequency, it will dampen out. So up here on the antenna, you have a superposition of all these different signals. But once you've transferred it into the tuning circuit, only one of those signals will proliferate, and that's the one that matches up with the natural oscillatory frequency of this RLC circuit. And if you remember, there is the expression that allows you to figure out what that resonant frequency is. Now, we have an additional problem, and the additional problem is that if you had a fixed capacitor and fixed inductors, you'd only be able to zero in on one station. That's not the case. You want to be able to tune to whatever station that you want. And so you need a way to tune. And the way you do that is by having a capacitor that you can vary. So this is the symbol for a variable capacitor. And in fact, some radios actually have variable inductors. And the way you can vary the inductance of an inductor is, if this is the coil, if you just take a piece of iron and you put it down the axis, if it's down a little bit, you get a certain inductance. If you put it in a little bit further, you will get a different inductance. So you can make an inductor into a variable inductor, but most radios use, or at least the ones that I've seen, use variable capacitors. And in fact, variable capacitors are really quite cool. I have this little breakout video that I'm going to show you that will sort of animate what these things look like. I've got a bunch of them back in Geppetto's workshop, and so I'm going to pull them out, and you're going to see them right now. And we're back. So you now have some kind of an idea as to how a variable capacitor works, which is good. We have a few more things to talk about. We haven't talked about how the radio station actually puts information onto its single frequency sine wave. We haven't talked about how the speaker circuit takes that information and decodes it so that you actually get sounds out of your radio. We haven't talked about amplification. These are things that we need to talk about, and basically we're going to talk about in the next video. And so I'm going to basically stop this video now. So more to come.